For the last week or so about interactions between molecules in a gas. And last class on Wednesday, we came to the big realization that when you turn attractions on in your gas, and we saw this in our simulator as well as mathematically, that when we applied this van der Waals approximation, right, which gives each of our atoms a shape and some attractions to each other, they fill some space. Once you kick those attractions on, we saw something very interesting happen. When you start to compress the gas, basically you have a fixed volume container that you're feeding in molecules. So again, this is increasing density in this direction. Right? Molar volume is inversely proportional to density, so low molar volume is high density. So we start to fill the gas with molecules. We start pouring in our CO2. This is CO2. At different temperatures, we see different compression curves, right? So at high temperature, we see this thing that looks like an ideal gas. It looks like the pressure is 1 over the molar volume, right? The pressure is inversely proportional to pressure is proportional to the density. It goes up like this, just like the ideal gas law would suggest. But as we start to cool, we start to see these non-ideal isotherms. Remember, an isotherm is a pressure volume curve at fixed temperature. So if you start to cool down, your isotherms start to deliver this kind of intermediate hump, which becomes so significant that there's a given temperature where the hump becomes flat, right? You get, no longer do you have a monotonic dependence on pressure, right? But there's a pressure and a volume where there's no change, right? You have a derivative here that's flat, right? It's flat there. In fact, it's an inflection point. It's not neither a minimum nor a maximum, right? It can't be a minimum because there's a point to the right that's lower than it, and it can't be a maximum because there's a point to the left that's larger than it. So it's neither a min nor a max, but the derivative is 0, but the second derivative is also 0 at this point as well. And of course, my microphone got it. There it is. Right, so we have the first derivative is equal to 0 there, and the second derivative is equal to 0 there at that point. That's a very strange point, right? Think about it here. The first derivative is always non-zero, and the second derivative is always positive. It's always pointing in this direction, positive curvature. And here we've got somewhere that not only has no curvature, but is flat there. And so something weird happens at this point, which I've identified as this critical point, right, which is a temperature and a pressure where this basically where everything kind of flattens out, this isotherm flattens. And then when we start to cool past this critical point, which for CO2 is about 31 Celsius, what we observe is an increasing region where the pressure dependence becomes flat with respect to density. So as you start to fill in molecules, the pressure doesn't change anymore. And we all correctly identified after a little bit of thinking that what's happening here is you're feeding, let's say here 22, you're feeding in gas, the pressure is increasing as you feed in gas, but eventually you hit a point where there's so much pressure and the temperature is low enough that the attractions went out and you condense. Right? So what you're observing here is feeding CO2 gas into your container, and it's just condensing out onto the bottom of the cylinder. Okay? And eventually you fill up that liquid layer until it equilibrates, and then it becomes you've basically formed a liquid here, and it's basically incompressible. We'll talk more about that today, or this week. And as you go down in temperature, that region, that density region where condensation happens, gets bigger because there's less and less heat and more net attractions. And therefore, you get a larger region of your pressure volume space where you get condensation. Okay, so liquids, right? We've identified this as the formation of a new phase, a liquid phase that does not couple to the gas. Right? It doesn't change the pressure at all of the gas, so it's basically got nothing to do with the gas. But it is sourced from the gas, and the only time that this appears is where you turn the attractions on. Right? Liquids occur solely because of attractions between molecules, and also the fact that they have a size. So what I want to do is to start thinking about this transition. Right? We have something magical happening in our gas that causes it to change its phase. Right? We need to start thinking about the thermodynamics of this. Because one of the weaknesses of this, right, is that we understand how the gas functions as a function of density. Right? Right? These are the responses of the gas inside the chamber. But all of this is showing you what how the gas reacts to your change of the system. It doesn't tell you anything about the liquid. The only thing it's telling you about the liquid is that it's forming in this region, that you're condensing. You have no idea of anything about the physics or the chemistry or anything about the actual liquid itself. Right? So this is a purely gas phase approach. And I want to learn something. First of all, I want to learn about this transition. How does the gas condense into a liquid, and what are the thermodynamics of that condensation? Does it absorb heat? Does it emit heat? Is there no heat change? Right? What are the characteristics that we observe thermally or energetically for this process that we observe in our isotherms? Okay. In order to do that, we're going to have to come up with a couple of new tools. Right? And the tools that will come up with this are ones that we'll use for the rest of the class. In fact, they're the ones that you use in all of chemistry. Right? So we need to come up with some universal way to measure energy changes, thermodynamics, of our liquid gas system. Not just the gas system, that's what this is, but the liquid and the gas together. Right. So we're going to step away a little bit from the nitty-gritty chemistry details for a minute to come up with this tool. I'll introduce one today and one on Wednesday that'll allow us to track these energy changes and to think about the liquid and the gas on equal footing. Right? That's the important thing. How can we talk about the liquid now? Okay, so let's set up our box, all right? And let's set up a box that allows us to think about the gas and the liquid together, okay? And we're going to use this. We're going to use our chemical intuition for this, okay? All right, so we want to study thermodynamics of the liquid phase and gas phase. Right? And eventually we'll want to consider all phases, right? We know there's a solid in phase in here lurking around that we haven't even explored yet. Right? So we want something that allows us to kind of not worry about phases, something that allows us to think about all the phases in our system, if there's more than two or one, at the same time. Something that allows us to talk about changes in all of them. All right, and again, I like to set up a nice convenient box for us to do this work, all right, to do these measurements. And lately, we've been thinking about boxes that are isothermal, right, where you put a sealed box inside of a bath at some temperature. The box, nothing can leave, right? It's completely fixed, right, and completely closed except for heat, right? This might not be the most convenient way to think about liquids, right, or boiling or condensation. Right? So maybe we want to think of a more practical way to build a box that allows us to measure heat transfer between the liquid, the different phases, and so on and so forth. That allows us to take advantage of the phase transition. All right? So to kind of avoid any extra complications, let's just try to focus on a box that really gives us the information we need about the phase change or the phase behavior. And the box we're going to use is the classic chemistry box. All right? It's going to be a flask or a beaker. All right? I'm going to have a flask, and this looks more like a liquor bottle than anything. Right? And it's going to be diathermal. Right? We're going to put this box inside of a container that allows us to equilibrate it at some temperature. Right, so the green is my little bath. Right, it's floating in this material. That's a bath, say a water bath. Right, this is a bath at T. Right. And this material, all right, so the flask is diathermal, right? So heat is allowed to transfer through the flask. Right, so this is heat. Right, so we have a diathermal flask. But we're going to leave the top open. All right, we're going to leave the top open to maintain a constant pressure. Okay, so inside of this liquid, inside of this flask is some material. Let's do a different color. Let's do red. All right, so we have some material in here. This is our material. Right, and we're going to, and again, there might be some liquid and there might be some gas in here, right? There might be some equilibrium of gas and liquid, as we saw. Some gas, some liquid. But we're going to supply a constant pressure from the outside, P external. All right, so P external, so let's define a few things. So T is our bath temperature. We'll just say, for instance, that our material is some gas, A, that is in equilibrium with its liquid. Okay, so it's a gas and a liquid. Maybe it's got solid, we'll worry about that later. And P external is the external pressure, let's say, of the atmosphere. Constant pressure. Right? E.g. the atmosphere. Okay, so if we evolve a gas inside our flask, right? Let's say for instance we're boiling it, right? Or something like that, right? We're boiling or creating evolving gas out of our system. Right? Some of that gas will exchange with the air. The air will come in order to maintain that pressure, right? So the pressure above the material, if you will, above the liquid layer, and including the surface of the layer, or the surface of the liquid, it feels exactly 1 atmosphere, or whatever the external pressure is. Okay, so what that means is that because this is an open system, right, molecules can fly out of here, and air molecules can fly in. It's somewhat of an open system. But the important thing is that the pressure never changes. Okay, we'll have to think a little bit later about this system when we think about how the material exchanges the outside and flows out. That could be a problem. We don't want to lose our material. But we're just going to make this approximation today because I think this is chemically the most relevant one because we do this all the time, right? This is literally what you do when you boil water on your sink, on your oven, your stove, excuse me, your stove, or when you go freeze an ice tray, right? Same exact process. Right? Your bath is your heater, that's a heating, it's a 212 Fahrenheit or whatever it is, or your freezer is acting as the bath at 0 Celsius or whatever the temperature is, but the pressure is constant, right? Constantly exchanging. Right. So this might seem like a real box to you. Right? We've been talking about these magical closed boxes, which are great and they're controllable, but now we have this kind of slightly more complicated system where things can exchange in terms of pressure. Okay. So now, again, remember the idea is that we've built a box. Now we want to come up with a function that allows us to describe the box. Right? We have a pressure, we have a number of molecules, we have a temperature. Right, we need some function that gives us, say, the energy of the system, something that's a state function, something that we can track, calculate integrals on, that's path independent, that allows us to track changes in the system, right? Changes in energy in the system. Right, but we can't really use the same equations that we use for the closed box because the closed box is not a constant pressure, right? The pressure is the response of our closed box. Remember that in our closed box, so let's just think about what our natural variables are here. So in a closed box with no heat, with no bath, right? So this is a completely closed box. This is the first box we looked at in class. When I write it like this is closed. In a closed box, right, we came up with our set of natural variables and we said that the total energy of the system is a function of the number of particles, the volume of the box, and the entropy. Right? Right, that's our natural variables. And how does that change when we go to a box that's allowed to exchange heat? Well, when it's allowed to exchange heat with a bath, oops, sorry. The screen went crazy. So now when we take this box and get rid of this and allow it to exchange heat instead, heat goes through. And we put this in a bath, so I'll just kind of put it like this. Right, this is what's called a diathermal box, or an isothermal box. We don't have to use entropy anymore. It's not our natural variable, but rather the temperature of the box, or rather the temperature of the bath. Right? So our natural function to track this box is N, V, and T. Okay. So what are our natural variables for our system, for our flask? Well, certainly N will be a matter, right? Because if you think about the heat that boiling generates, if you double the amount of boiling molecules, the heat is twice as much, right? Makes sense. Right? So certainly N is a function. Certainly T is a function, because again, the bath is at some temperature T. It's constantly exchanging heat to the bath, right? But not volume anymore, right? The reason why volume isn't fixed is because now the system is exchanging pressure with the outside environment. There really isn't a well-defined volume. Basically, the material has to fill up whatever available volume there is. All right, but the amount of material that fills it up is dependent on how much pressure you have coming in. Right? We'll look at that more carefully about that. But volume is no longer a well-defined concept. It just requires enough energy to fill the space, but depending on the pressure, the amount of volume that fills depends. Right? So we can't use volume anymore, but we can use pressure instead. Right? So the natural variables for this are U, the total energy of the system, which is a function of N, P, and T. NPT instead. All right, we've swapped volume with pressure as our input variable. All right, so what that means is that the volume now is an extensive property of the box, not an intensive one. The pressure that the gas fills of your material is defined by the external pressure from the atmosphere, or whatever the source of that pressure is. Right, so now it's P. Right, so that's going to change our equation a little bit, right? It's going to change our equation, our TdS minus PdV. That's not going to work anymore because V is no longer a variable of our expression. Okay. Now there's an entire mathematical formalism called Lagrange multipliers that allows you to convert between all of these. We're not going to learn that in this class, okay? So we're not going to learn Lagrange multipliers. But there's actually a natural way to convert from V and P. Right? These are what are called conjugate variables. Right? We learned that, remember that pressure is a derivative of volume, right? The change of the energy with respect to change in volume, du dv, is the pressure, right? That's how we define pressure, du dv minus P. And we can relate the derivative of the volume with respect to pressure in response to V, right? It's going to be a function of V. So du dv is pressure in this case, minus pressure, and here du dp is volume. Right? They're conjugate variables of each other. One's a derivative of the other. You can replace them with each other like that. So I can always make swaps between P and V. I can make swaps between T and S. Remember, because T and S are conjugate as well. Remember, temperature is defined by the change in the energy as you change the entropy. So this is a response. These are response variables. T and S are responses to each other, and V and P are responses to each other. And you can swap the order of them, how you choose one as an input, one as an output. Okay, so it's called a Lagrange multiplier. We're not going to go through that math. But the idea is that they're naturally related to each other. Later, when we take next class, we'll learn how position and momentum are conjugate, and energy and time are also conjugate in the same way. Right, so what I'm basically saying is that this is an allowed thing to do. We can do this, right, mathematically. But we have to see what this function u looks like, right? It's important that we think about what u looks like. Right? What do we learn from it? Right, what does the energy look like for this thing? Okay. So let's go to the next page. Okay, so for our open flask, at constant pressure, all right, this term constant pressure has a different term, a more physical term or more kind of standard term for it. This is called isobaric conditions. Right? Iso again means same, and baric means pressure, like barometer. Right? So isobaric means no change in pressure, same pressure. Isobaric. And we're going to do this at isobaric conditions. Okay, and we know that this function u, we know that the energy of this system is a function of n, p, and t. Okay, we just have to figure out what it looks like. All right, just like we did before. And let me get my notes in the right order. Okay, so so we can take the original function u of nv and s from our closed box and do these magical Lagrange multipliers and come up with a new function that defines our energy for this system. Okay, I'm going to skip that step and go right to the final, go to the function that you come up when you make that change between v and p. All right, and you come up with this new function that defines the energy. And I'm just going to give you that result here. If you take a more advanced thermodynamics class, which I doubt any of you ever will, you'll see this. In a physics thermo class, you do Lagrange multipliers. It's not important for us here. All right. So this function, so we define what's called a new, so we take this idea, we define a new thermodynamic function. Which is called h. Right, this is our new function h, which is a function of n, p, and t. And this is equal to u plus the pressure of the system times the volume. Okay, so we're going to take the total energy of the system, and we're going to add this PV term to it, this work term. Right? Remember, P times V is work. All right, so if you just think about it really roughly, remember that. So let's just kind of look at what this is. First of all, I'll give you the name of this. All right, this term, this is what's called the enthalpy. Right? And we can kind of roughly think about this as if we remember that the fact that du is equal to T ds minus P dV. Remember, that was our first postulate many weeks ago. Right? And you can kind of, if you integrate all the d's out, you can kind of see that this looks like u equals Ts minus PV. Make sense, right? I'm just getting rid of the d's here. Right? So it kind of looks like u equals Ts minus PV. Right? So if we take this and add PV, right, we'll see that enthalpy has something to do with the heat content in the system. Right? If I write just kind of roughly, this is just a very rough calculation. I'm going to put little quotation marks here. I'll put it at the end. This would be the same as Ts minus PV plus PV, which looks like Ts. Okay, so just by looking at this, we have to be a little more careful about this because derivatives don't work like this 100%, but we'll have to be more careful that this is correct. But the idea is that enthalpy says, right, it says that enthalpy has something to do with the heat content of the system. Okay? Basically, the idea is that when we put our liquid into our flask, our material that's both gas and liquid together, maybe it's just one or the other, and we let it fill the space, okay, right, and it equilibrates with the external pressure, okay, it's done all of the PV work it needs to equilibrate. All right, so we want to think about what's left over, right? What's left over after it fills the flask and maintains its volume and pressure? Well, let's just subtract off that PV, and the enthalpy is whatever's left over after you've completed that filling. Okay, it's the remaining heat energy of the system at constant pressure. Right, so a good way to think about this right now, and we'll prove this in just a second, is that enthalpy is the heat content at constant pressure. All right, let's show that that's the case. All right, let's do a little bit of math. All right, let's prove that. All right, let's do a proof. Really, really simple calculus proof. Just derivatives. Proof. Okay, so let's take our enthalpy, all right? Let's say the system has an initial enthalpy H, and we perturb the system a little bit by adding or removing some heat, dH. Okay, so we're going to maybe crank the temperature up a little bit. Maybe we're going to turn temperature down. Maybe we'll do something else to the system, right? We're going to change it a little bit, okay? So we're going to move dH. All right, so how does the enthalpy change when we move dH? Well, that means that this change, the U might change by a small amount, right? And P might change by a small amount. And volume might change by a small amount. Okay? Right? And I'm not going to hold this constant pressure yet, right? You might say, hey, dP is 0, right? So this should go away. Let's hold on to that and let's apply that assumption at the end. Right? So let's just assume everything can change in our system. U, P, and V. Right? The system, right, maybe when you boil, right, when you boil your gas, you start to heat it up, the pressure is going to start increasing, the volume is going to expand. Maybe as it gets colder, the volume gets smaller because it becomes more dense. Right? There's lots of different ways that this can change. And so let's just do a little bit of algebra 2 and FOIL this out. You get U plus DU plus PV plus PDV plus VDP plus the change in pressure times the change in volume. All right, I just did a little bit of FOIL. All right. All right, I'm going to rearrange these terms a little bit. So this is U plus PV plus DU plus PDV plus VDP plus the second derivative with respect to volume and pressure. Okay, but we can simplify this further. This right here is H, U plus PV, right? So we have H on the right-hand side. So we have, that means that we have H plus DH. Well, on the left-hand side of this equation, we have H plus DH, right? And so we have H on both sides of this equation. So we can cancel that out. And we're left with therefore the change in enthalpy is equal to the change in the total energy plus PDV plus VDP plus dPdV. Okay, so we have this equation, but now we can apply dP is equal to 0, constant pressure, right? So this is equal to 0. This is equal to 0. This is constant pressure. dP is equal to 0. Right? And what are we left with? We're left with dH, the change in entropy, or enthalpy, excuse me, is equal to the change in energy plus PdV. Okay, so let's just look at this equation, right? Right, and relate it back to our original expression for the total change in energy, right? The total change in energy is the heat content minus the change in the work. Here's the change in the work. Here's the total change in energy. So what does that mean dH has to be? It has to be TdS, right? Because if I subtract PdV from both sides, I have dH minus PdV is equal to du. du is equal to TdS minus PdV. That means dH is TdS. So by the first law of thermodynamics, this says that dH is equal to TdS. All right, so enthalpy at constant pressure is the heat change of the system. Okay, we subtract out all of the changes in, volume and pressure. When you take a gas, you have a condensed liquid and you boil it, you're going to have a big change in volume, of course, when you do that. Right? There's going to be some energy change due to that work. Right? Enthalpy records everything once you get rid of all that junk, and you're just left with the heat. Right? So it gets rid of all the PV work. All right, so enthalpy, right? As I said, as we proved here, enthalpy is the heat content of your system at constant pressure. Okay? And so changes in heat, measured changes in enthalpy are measured changes in entropy, right? dH is proportional to ds divided times T, right? It's the heat content of energy. All right, so that's really, really powerful if we can come up with some ways to measure enthalpy. Right? If we can measure this some way, we can measure S. Right? Once we know S, we know everything about our system pretty much. Right? So enthalpy allows us to think about this at constant pressure. All right, so what we're going to have to do is come up with a set of tools that allows us to use enthalpy as our analog for energy here, right? Because when the system changes, so let's say you're boiling or condensing a liquid, you don't really care about the energy content of taking the volume of that gas and putting it into the liquid, and vice versa. That's not really all that important, right? It is in the sense that you have to fill the physical space with your new gas. But in terms of the chemistry of the system, right? You're thinking about chemical changes, physical changes of your material. We want to get rid of all of that, right? We don't care about that because in general, 1 mole of gas, regardless of the gas, roughly does the same filling, right? Up to a certain point. They're mostly ideal, right? You assume ideality. All gases fill the same. So let's just ignore that, right? We don't care about that energy. That's just going to happen whether we like it or not. What we care about is the energy that's available in the system for us to maybe do something else with. Right? Does it change the heat of our bath? Does it absorb energy during the process? Does it emit energy during the process? And that's independent of the PV work, which we don't really care about. Right? So enthalpy is really powerful from that, but we're just going to have to come up with some way. And again, I can come up with all these functions, H and S and all this junk, but if you can't measure it, then what's the point? Right? So eventually we're going to have to figure out how to measure this. And that's turns out to be much easier than measuring this. Right? Entropy is much harder to measure than enthalpy. In fact, you'll be measuring enthalpy in lab starting this week. Okay, so let's do a couple of examples. This is kind of I want to give an example about how H has this change in heat, but there's also this PdV part. Right? How do these things balance? What does the enthalpy actually measure? So I have 2 different examples I want to give you about calculating the enthalpy of a process. And we'll see where that PV, right, when you boil a gas and change the volume, where that plays in the energy calculation. All right, so let's look at an interesting problem. All right, let's do some chemistry. Okay, so let's, let me sign, hopefully this time now that I have this digital box, I can actually show you what these look like. So what I want to look at is the change between two different types of minerals, calcium carbonate minerals. So let's look at calcium carbonate. There's different what are called allotropes of calcium carbonate, different types of minerals in the crystalline form or solid form. One of them is called calcite. Let me find a picture of calcite for you. I've never done this with pictures. It's nice to actually have pictures. You've probably seen calcite if you've ever been in a cave. You've seen calcite before. Will this display? Maybe not. Just a sec. They kind of look nice, don't they? All right, let's see. There's a beautiful picture on Wikipedia of this. And so here's a picture of calcite. Different types of calcite, but is calcite all the same? They have roughly the same structure. Right? You know, the stalactites and stalagmites and all that junk. That's mostly calcite and lime. And then I'm going to look at the reaction to convert it to a different allotrope of calcium carbonate. There's a different form of solid called aragonite. And let me find a nice picture of that for you. And aragonite, again, kind of has a similar structure to calcite, a similar color, but it tends to be more pink, traditionally. Maybe I can get Dr. Luzik to come in here and tell us about the differences. If you didn't know, Dr. Luzik loves minerals. All right, and these each have different densities. All right, so the density of calcite is 2.71 grams per milliliter. And the density of aragonite, slightly denser, is 2.93 grams per milliliter. Okay? And what you can measure is that the change in the total energy of this system, when you go through this, is plus 0.21 kilojoules per mole. Okay, so the total energy change is 210 kilojoules per mole. And what I want to calculate is how much of this total energy change is just heat, right? What's the heat content, which is delta H minus delta U, right? We're going to subtract out the PV, right, the heat content. All right, because there's going to be some energy required. There's going to be some energy required to rearrange the crystalline structure of calcite in order to form aragonite, right? Crystals have kind of a fixed mono structure. Each unit of a crystal is a fixed structure, and so you've got to rearrange the atoms in here to form these, okay, the different crystal structures. All right, so that's PV work, right? You have to rearrange the system. It gets smaller, it gets bigger because, I mean, you can see it here, right? The densities are changing, right? So the PV part, the work part of the material is different, right? And that's and so part of that work change to change the size and the shape of the material is accounted in here. The question is how much of this energy is this heat, right? The heat of the reaction, the actual heat of the chemical change, not just the amount of work it requires to rearrange the material and fill the space. All right, and we're gonna do this at 1 bar, which doesn't really matter, but I'm just gonna put there just in case because we need the pressure. All right, so how do we calculate this? All right, well, remember enthalpy delta H, like any other thermodynamic function, is a state function, which means it only depends on the final and the initial state. Bless you. So that means that the change in the enthalpy of the system is going to be the enthalpy of the final state, which is aragonite, minus the enthalpy of calcite. Okay. This is just Hess's law. If you remember Hess's law from 1.5 million years ago, calculate the enthalpy of a reactions, the products minus the reactants, right? This is the same concept. Okay, so let's go ahead and calculate this. All right, so DH, we're going to do a delta H because we're doing a big change. That's going to be the H of the aerogin. I'll write that HA minus HC, calcite. And that's going to be the total energy of the aragonite plus the pressure times the molar volume of the aragonite minus the total energy of the calcite plus the pressure of the system of the sample times the molar volume of the calcite. Okay, and I'm just going to combine like terms, right? This is UA minus UC plus PVA minus PVC. Bless you. Right? And this is equal to the change in the energy, total energy, minus the pressure times the change in the molar volumes. Let me do that in a different color to make it more obvious. Right? So the enthalpy content is exactly what we expect. It's the total energy minus the change in the work that it takes to, form a crystal of this size versus this one. Some difference in the densities, right? I mean, if you can see the PV term has something to do with molar volumes. Remember, molar volume is 1 over the density. So this has something to do with density change as well. Okay, and so we can always, because they're related, we can always write that the molar volume is the molar mass of the material divided by the molar volume. Divided by the density. By the density of the material. Right, this is the molar mass. All right, and that'll give us units of moles per gram, moles per liter, which is exactly what we want. Liters per mole, which is exactly what we want. Okay, so when we bring all this in, all right, I'll subtract off delta U from both sides to get delta H minus delta U, which is equal to minus P delta V, which is, once we plug in our formulas for densities, we get minus, we don't get a minus here, we get it, yeah, I'll keep the minus, minus the pressure times the molar mass of the material times 1 over the density of the aragonite minus 1 over the density of the calcite Do I have that the right way? Yeah, I have that the right way. And just canceling out, that's PM times 1 over the density of calcite minus 1 over the density of aragonite. Right. Okay, I'm gonna have to put a new page on here. So this is our formula for the difference in the enthalpy and the total energy, right? So it's going to tell us something about the heat content of our system. And as you can see, it's different. It's proportional to the change in the densities, right? That's going to be, rather this is the, sorry, it's not the heat content, but rather this is the PV content, right? Delta H is the heat content. We're subtracting off the heat part of delta U, and we're left with an equation that's just a function of the two different densities, right? How the volumes change. Right? It's just PV work. They're just changing. Right, so this is the PV work for the reaction. This is the PV work required for changing allotropes or changing crystal structures? All right, so let's evaluate this number, all right? I'm going to go ahead and put it on the next page. All right, so we have delta H minus delta U is equal to the pressure, the external pressure, times the molar mass of our stuff, minus 1 over PC minus 1 over PA, rho A. Okay, and so I gave you all these values. The pressure external is going to be 1 bar. All right, we need to get that into metric units. So 1 bar is equal to 1 times 10 to the 6 pascals. So megapascal. So we're going to multiply that by 1 times 10 to the 6 pascals per bar. All right, we calculate that in terms of the molar mass. We need the molar mass. The molar mass of calcium carbonate I know by heart because it's really, really easy to remember. It's exactly 100.1 grams per mole. It's a really easy one to remember. And now all we do is take a difference of our densities. Density of the calcite is 2.71 grams per cubic centimeter, grams per milliliter, minus 1.293 grams per milliliter. All right, so what are our net units? Well, let's see, the grams cancel out, the bars cancel out, and we're left with pascals times milliliters. We'll have to convert that to liters, and when we get to Pascal liters, that gives us joules, as we'll see in a second. Okay, so this number right here is, let's see, this is big minus small. This is a positive number. This is 0. Oh, sorry, let me change that. Wrong units. So in our units, this is plus 2.8 times 10 to the 5. Pascal milliliters per mole. All right, and now we need to convert this into metric units. So we have to convert milliliters to meters cubed. All right, so how do we do that? Well, there is so let me replace the ml with cubic centimeters. Right? It's the same thing. And we have, let's see, we got here with centimeters. So centimeters are going to be in the bottom of our dimensional analysis. And how many centimeters are in a meter? 100. Sorry, there's 100 cm per 1 meter. And we got to cube it, right? Because you got to get meters cubed. Okay, so our final number is going to be this divided by 100 cubed. 100 cubed. And this leads to 0.28 Pascal meter cubed per mole. And this is a pressure times a volume, 0.28 joules per mole. Right? Pascal meter cubed. I'll just write that. Pascal meter cubed. I'll put it here. Pascals times meter cubed is a joule. Okay, so it takes, what that means is that it takes, well, let's see, we're going from aragonite to calcite to aragonite. And so we're going from a dense material to a lighter material. Okay, so the system is expanding, right? And an expansion causes a negative drop in energy. So the sign on this is incorrect, but basically this means that it takes 0.28 joules per mole to take that calcite crystal and convert it into aragonite. The positive, right? So positive. It takes 0.28 moles to compress the calcite into the aragonite. Sorry, the other way around. The calcite into the aragonite. Right? Takes that much. Right? So that means then, so let me just write that down. It's just, right? So it says here that delta H minus delta U is on the order of 0.3 joules per mole. And delta U, right, we wrote that down at the beginning. Sorry, I just lost it here. Here it is. Is plus 210 joules per mole. Right, so what does that say? Well, it says here that the PV work required is negligible relative to the heat requirements. Right? There's only 0.3 joules a mole needed to do the work change, to change the physical space of the crystal. And so all the rest of the energy change, it has to be entirely heat. Right? So what that means is that if your volumes aren't changing that much, and your system is around 0, then delta H is approximately equal to the change in the total energy. Right? That's really powerful, right? So if we have a process where basically, say you're going from solid to solid or liquid to liquid, right? Think about any chemical reaction, right? You have HBr, CH3OH, methanol, and HBr. That gives you CH3Br and NaOH. That's a really bad reaction, but just by and large, think of that, right? You have an organic chemistry reaction. What's the molar volume of your products? Well, it's a hydrocarbon, it's a little less dense than water. It's got some molar volume, it fills up some space. And what about the products? Well, they're not really that much different, right? They're still hydrocarbons, they're still organics, they're maybe a little volatile, but the densities don't change that much, right? You're not going from a very not dense liquid to a very dense liquid. They're generally about the same. And so the PV work required to do a chemical reaction in the solution phase is negligible. Right? So then we can just say, well, if we can measure delta H, then we know everything about the energy change of the system. We just neglect the PV change. Okay, so the idea is that in homogeneous systems, condensed systems, so in homogeneous and condensed processes, right, this means that delta V bar is close to 0. Sorry, that's wrong. Condensed means high pressure. Pressure density greater is larger than 1. And homogeneous means the change in the volume is basically 0. Everything's kind of mixed nicely. The enthalpy change we measure is basically the energy change we measure. Sorry, enthalpy is almost, sorry, let me write this more carefully. I'm sorry. Enthalpy captures the vast majority of the change in energy. Total energy. Okay. All right, so that's why in chemistry, when you do organic chemistry, we never even think about delta U, right? Probably the first time you've ever think about total energy of the system, right? You just go straight to enthalpy, right? Enthalpy, and then when you do Gibbs, you have entropy that you have to consider as well. We'll look at that next class, or hopefully, right? So this is the assumption that we make in chemistry most of the time. All right, let me show you a place where this breaks. All right, let's do a really, really simple calculation. Even simpler than the last one. The last one was mostly just conversions. All right, so really, really simple reaction. And this isn't really a calculation question. It's just kind of an argument. All right, so let's look at example 2. All right, so let's look at the reaction, the classic water forming reaction between H2 and O2 to give 2 H2O liquid. This is a highly exothermic reaction. This is one of the reasons that when you pop a balloon full of hydrogen, it goes like that, you know, it explodes. A very exothermic reaction releases a lot of heat. Right. We'll look at this, actually, we'll look at this reaction very closely when we get to kinetics. Very interesting reaction. But let's just ask some questions about the energy. What is delta H minus delta U for this? All right, so the important thing to notice here is that we're going from gas, we have 3 mole equivalents of gas to 2 mole equivalents of liquid. All right, so we have a big PV change here. All right, we're going from a very dilute gas to a condensed liquid at very, very different densities. All right, so let's just kind of get a sense of how much that density, how much that work difference is. All right, this is the work required. Okay, and so delta H minus delta U, by definition, is the change in the PV work. Okay, and so what we have now is a liquid. So we have 3 moles of gas going to 2 moles of liquid. Okay, and so let's think about how the PV changes from the point of view of the gas as it condenses, right? So this is in terms of the gas delta PV, right? And so we could write this as delta nRT instead, right? We can assume ideality. So let's assume an ideal gas. Right, and so how does nRT change as this process happens? Well, T is fixed, and we're going to assume a fixed T. All right, R doesn't change, it's a constant. So the amount of work that's being done is proportional to change in moles of the gas. Right, so we can simplify this as delta N times RT, right? And this is because dt is equal to 0. We're fixing the temperature. Okay, so that means that the amount of work required is this is the amount of mole. This is the change in gaseous moles, vapor moles. Right, and that therefore, right, we lose 3 moles of gas to form 2 moles of liquid. So delta H minus delta U is equal to minus 3 RT, right? Because delta N is equal to minus 3.
I have a question.
Yes, ma'am.
So, like, I guess I'm confused why you're able to assume that the temperature is constant. Because I thought, like, in the last question we were doing, the whole thing was that, like the temperature wasn't.
Ah, well, okay. Well, so maybe it's a good point. So the temperature may be changing, but the temperature is subtracted out because we've minus out all the heat content in this difference. So the temperature difference is irrelevant. Okay. Because if the temperature changes, that's going to change the heat content of the material. And that's just delta H. That's also a delta U. TDS is in both of these, and we're subtracting them so it goes away. So there's no T dependence anymore.
Okay.
So just to make Monica happy, I'm going to put a little squiggly line in here and say, approximately that. All right, and of course that's easy to calculate, right? That's minus 3 times 8.314 joules per Kelvin per mole times 298.15 Kelvin. All right, and that's roughly 24 times 300. I'm just going to do it really quickly myself.
So that's 3 times 8.314 times, let's just round that to 298.15, yeah. Yeah, so that's minus 7.4 kilojoules per mole. All right, so as you can see, a significant amount more of energy required to do this change, the physical change. More of the energy is being used for that volume change because you've got to change from a very dilute gas to a very condensed liquid. There's a big delta, big work difference. Maybe it's worth thinking about how much of this is due to, right, so it takes 7.4 amount of work. What's the heat content of this, right? What's the total change in energy, right? So let's compare that to how much heat is being released in this reaction. All right, so we'll just use the old school chemistry calculation, right? We're going to calculate the enthalpy of the products and subtract it from the reactants, okay? I'm going to go through this process more carefully on Wednesday, but let's just do a quick check. All right, so let's just see roughly what this comes out to. All right, so now I want to calculate delta H, and delta H is going to be the enthalpy of the products, 2H2O liquid, minus the enthalpy of the O2 plus the enthalpy of the H2. And there's some numbers here. Yes, there's a 2 here, and there's a 2 here. All right, got to multiply by 2. All right, so let me show you where I'm going to look these up. I'm just going to show you really quickly, and then on next class we'll actually go through this more carefully. I'll show you these resources. They're really, really nice. So let's go ahead and look up these numbers. All right, so I'm going to show you this website again on Thursday or Wednesdays. This is called the Active Thermochemical Tables. I want to define what all of these numbers mean first, but let's just look them up. This is a place to look at for enthalpies of all basically common materials. Right? Really, really accurate numbers. Right? I don't want to tell you exactly how we calculate these numbers precisely until Wednesday, but we'll just take them as is. So we'll go to the most recent version of the data, and I'll walk through this website again more carefully on the next class. And let's go look for the enthalpies for hydrogen, oxygen, and H2O liquid. The first result on this list is dihydrogen, H2G. It has an enthalpy of 0 by definition. All right, so let's remember that. Just write that. Let me just go ahead and Alt-tab over. So this one is 0, so we don't need that anymore. Let's look for oxygen on here. Here's dioxygen, O2. It has an enthalpy defined as 0 exactly. I'll talk next class why it's defined exactly at 0. All right. We'll have to figure that out. And now we just need to think what the H2O one is. And here we go. So here's the liquid, H2O liquid. This is crystalline. Oh, this is ice. I'm sorry. That's ice, crystalline. Sorry, where's liquid? All right, let's just type it in. Sorry, I got to be careful. Ah, here it is. Oh, it's the same one. Okay. All right. Yeah. So the enthalpy for H2O is minus 285.201 kilojoules per mole. All right. So the total enthalpy is this difference. So we multiply this number by 2. So that is the total enthalpy of this reaction, the heat change of this reaction. Right. This is the heat change of reaction. Is going to be 2 times this 285 number, 201, which is minus 570.4. We'll just write that kilojoules per mole. Okay, so as you can see, right, so this is the heat change of the reaction, and this is the work change of the reaction, right? So the system, in order to condense, so this is the work, PV change in this reaction, and this is the heat change, sorry, of the reaction. So as you can see, right? In order to compress two gases to form a liquid, you've got to put in a decent amount of, the system has to expend a decent amount of energy to do that, or release a decent amount of energy to do that. Right? 7.4. Compare that to the two crystals, right, which barely even scratched joule. 0.2 joules, right? But big density difference here, big pressure difference. There's going to be a lot of PV work. But compared to the heat change of this reaction, it's still pretty minuscule. Right? It's about 1.5% of the total energy change, the work, but it's appreciable, right? So when you're working, the kind of lesson here is that in reactions that are very exothermic, like H2 plus O2 goes to H2O, which releases a lot of heat per mole. Again, we can kind of neglect the work a little bit. But what you would find from this is actually that if you were to go measure, like we'll do this calculation next class, we'll think about this, is how do we measure this heat change? Well, you're going to measure it by measuring the temperature change of the material, right? It's going to release that heat, and your bath temperature may change. The thermometer in your system changes temperature as it releases this heat. And you might find that, again, the temperature difference that you calculate upon this reaction isn't exactly what you get from your thermometer, because you haven't accounted for the fact that some of that energy is being used or released for work as well. Right? So this energy, if you will, does not appear on the calculator, or sorry, on the thermometer. Doesn't appear on the thermometer. This work is being done to fill the system and equilibrate it to the flask when you make that change. What you observe on your thermometer is just the heat change. Right? That's what we would observe. So if someone were to ask us, hey, what's the total energy change in this reaction? We would also have, in order to get the right energy balance, right? Think if we're doing this industrially and we need to balance input power to output power, that we're going to have to consider that we're going to be off by about 2% if we just think about the heat change of the reaction. Because there's an appreciable amount, 2% of the energy, total energy in the system is being used to compensate for the phase change as well. Okay, so yeah, go ahead,
So
please.
I'm confused compared to the last one that we did. Like, I see obviously the value being like negative is different, but I'm saying like
In terms of percent?
Yeah, because you're still getting like a small.
Yeah, it's a small difference. All right, so let's calculate it. So this is, let's just do a rough number. All right, so this is 7.4 over 570.4.
No, I mean like, because in the last, because you were saying that this one's a different example, like in the sense of like, because the last one, we were talking about how when you do delta H minus delta U, you get 0.37 compared to delta U is 210.
Yeah.
So it's negligible, right?
Yes.
You're saying, but why wouldn't it be, because they're like equal here.
They're not negligible here. I don't know what you mean by they're equal.
Because like, when you do delta H minus delta U, if you get like a small number, then that means
Yeah.
the two are very similar
Yeah.
values. So here you still get a small.
Well, they're 2% off. What are they off in the other one? How different are they? So the work is 2% of the heat in this case. What is it in the previous one? 0.3 over 210. What percentage is that? I'll just do it for you. This is 0.14%. It's a tenth of the contribution as the other one, right? So by going from liquid to heat, the contribution due to the work difference to change the phases is 10 times more than it is for two solids. Now you might say 1% is not enough, not much. I agree, it's not much, but it's a factor of 10. That's a lot. In an absolute case, it's a factor of 10 is significant. Think about it, and again, these are things that are important at scale, right? Maybe in terms of chemistry in the lab, it doesn't really matter so much, right? Because you don't really have these balances, right? But if you're working on a system, right? Imagine that you're running. Okay, so, right? Imagine you're running. This reaction is what drives a hydrogen-powered car, right? You have a compressed tank. Actually, this is exactly what it is. It's the fuel cell reaction in a hydrogen-powered car. You have a fuel tank of H2 compressed. It's being fed into a reaction chamber, some sort of reactor in your system that drives your pistons. It's reacting with the air that's flowing in from the gas. There's a spark to ignite it. And the only thing that comes out of the exhaust is water. And whatever unreacted H2 and O2 you have, there's probably none of that. Just water. Right? And that engine, let's say that hydrogen engine is about 60% efficient. 50 or 60% efficient. So for every joule it creates, about half of that joule is used to drive the wheels. All right, so you got a 50% efficient engine, and you want to eke out every little percent of that engine. Let me tell you, those guys at Hyundai and stuff are always thinking about halves of percent and quarters of a percent and stuff like that. And here, if you do this calculation and you forget to consider the fact that the stuff has to compress into a liquid after reaction, and you've calculated how much energy that system releases, but you're off by 1.2%, the predicted efficiency of your engine is off by a total amount by 1.2% off of 50, right? And that's an error of 2 or 4%, right? Because your efficiency is off here to be 1.2%, so therefore your efficiency relative to 50% is doubled. Change is doubled, so a 1.2% off in your energy calculation leads to a 4% difference, roughly, or 2% difference in your efficiency calculation, right? It's doubled. So this is an appreciable amount on scale, at large scale, industrial scale, right? When you're really starting to work with, dollars and cents, or I mean, there's a reason why, people like Delta and American Airlines, they constantly penny pinch every pound, because I don't know if you know this, but just to put the little magazines in each of the, we call them the seat back pockets, the little crappy magazine where they sell you all that junk that you don't need. It costs American Airlines approximately, I want to say something like $250,000 or $500,000 a year in fuel, if not more, just to have those magazines in there. Right? So that's why they charge you, why they're so anal about your cargo size, because they penny pinch those fuel points by tiny fractions of a percent. And so if GE comes with an engine that says, hey, it's 50% efficient, but they forgot to consider the fact that work and heat might change, and that the gas is off, and you're off by 2%, then that's millions and millions of dollars out of American Airlines' pocket that they didn't originally anticipate for. Okay, so energy at scale is really important to consider all these really, really precise, accurate points. Okay, and that's really important when you're working with different phase changes like this. Okay, all right, so we'll come back to this. We'll kind of formalize everything, talk about the energy scale of chemistry, how we use enthalpy in chemistry, how we calculate it, and then we'll go from there.
So I wanted to just confirm. So with this, you're saying since it's a large percent, you have to consider energy and enthalpy. Okay. Okay. Thank you. I hope that question. I'm sorry, cut into the end.
No, that's fine. That was a good question. I didn't really have anything else to talk about today, so.
What'd you say?
All right, what's up?
So I have mostly finished the problem set.
Okay.
Because I talked to you about turning it in tonight instead of before.
Yep.
I have a couple questions on it. Would I be able to come into your lab tonight?
Yep.
Okay, cool.
Yeah, that's fine.
Because I don't have band tonight, so I can.
Okay, great.
actually-
Yeah, I'll see you then.
Cool, thank you.
You're welcome.
Because I think it automatically works for it.
I'm going to be a few minutes. Do you just want to walk over to my office and I'll meet you there?
Where is it exactly?
Oh, good question. Do you know where the vending machines are in the back of Eklund? There's those benches right there. You can just wait for me there.
Okay. Thank
Yeah,
you.
you're welcome. I'll be there in like 5 minutes, okay?